Here we are again. We're going to look at homework set 23. These problems are in chapter 8, the momentum chapter, 17, 24, and 25. Problem 17 is really quite straightforward. You have this one railroad car, and it's coming in with an initial velocity of 10 meters per second. And it collides with four identical railway cars, and you know I can't draw. And after the collision, all five cars are linked together and moving together. There's lots of wheels. And we want to know how fast they're moving after the collision. Now, this is an old exam problem, and what people had trouble with was the fact that we don't have the mass of the rail cars, and we don't need it. All we need to know is that they're identical rail cars, even though I didn't draw them very identically. They all have the same mass. And we know that in any collision, no matter how messy, that collision can involve C4 explosives. No matter how messy, momentum is conserved for a system as long as we include everything that collides or hits or interacts. In this case, as long as we include all five of those rail cars in our system, that momentum will be conserved. So I can say that the initial momentum is equal to the final momentum. Now, when you use this conservation of momentum, initial and final take on a very special meaning. With our energy problems, we got to choose what we meant by the initial event, the final event. You know, we could choose anything we wanted. But when you're doing conservation of momentum, that initial means right before the collision, and that final means right after the collision. You can't wait for the cars to slide across the pavement and into someone's yard, okay? Right after the collision. Now, before the collision, I had one car of mass M moving at 10 meters per second. Now you'll notice that these are vectors. Momentum's a vector. And so I'm always going to need a coordinate system. We'll call to the right positive x and to the left negative x. So this is going to be positive momentum. And I also have four boxcars not moving at all. See how I just wasted ink there? Now, after the collision, there's the collision right there. That's where the collision happened. After the collision, they're all moving together, so I can treat them as one unit that has mass 5 times the mass of a single boxcar. And they're moving at some final velocity that I would like to figure out. And so now I find that the final velocity is going to be equal to m times 10 meters per second divided by 5m. And so, as promised, we don't really care what the mass of a boxcar is, as long as it's the same for all the boxcars. So this m cancels out. And what I get is a final speed of 2 meters per second. In this problem, the total amount of mass that was moving increased by a factor of 5. And if the momentum was going to stay the same, that meant the velocity had to decrease by a factor of 5. It's that simple. Okay. Now, the next problem is a little bit more interesting. in this next problem, we have two blocks that are coming towards each other. I have a 4 kilogram block, and it's moving at 8 meters per second to the right, and it collides with a larger block. This is a 12 kilogram block that is moving at 4 meters per second to the left. Now, after the collision, we're told that this bigger block is moving 4 meters. Woohoo. No, we're not told that. I'm sorry. We're told that this small block after the collision is moving back at 3 meters per second. And what we want to know is what's the final velocity, magnitude, and direction for that large block? Well, this is a standard, actually it's the canonical collision problem. All collision problems are the same problem right here. And we solve them with conservation of momentum, where this momentum is for the system comprised of both blocks. And because this is a vector equation, I need a coordinate system, and I need to stay true to that coordinate system. Well, the initial momentum is just the momentum of this block plus the momentum of that block. Well, I've got a 4 kilogram block moving at 8 meters per second, and it's moving to the right, so that's positive momentum. I then have a 12 kilogram block moving at 4 meters per second, and it's going to the left, so that's negative momentum. There's the collision right there, that equal sign. After the collision, I have the 4 kilogram block moving at 3 meters per second, and it's moving to the left, so that's negative momentum. And I don't know whether that 12 kilogram block is moving to the left or the right. And so I'm just going to make that a positive variable. 12 kilograms times V final. I'm going to assume that it's positive. If I solve for it and I get a negative answer, I'll figure out that I was wrong. So this is going to be a positive 32 Franci. This is going to be a negative 48 Franci. That's going to equal a negative 12 Franci plus 12 kilograms V final. Now, this is going to give me negative 16 Franci is equal to negative 12 Franci plus 12 kilograms V final. And if I bring the negative 12 Franci over, I get negative 4 Franci is equal to 12 kilograms V final. And this is going to give me a V final of negative 4 Franci over 12 kilograms, or negative 1/3 meters per second. Now the magnitude would be the 1/3 meters per second. The direction would be the negative sign, or left. So I could write this as negative 1/3 meters per second, or I could write 1/3 meter per second left. But I have to choose one or the other. I have to either write it this way, or I have to write it that way. I can't say minus 1/3 meter per second left, because minus left is right. And I don't mean correct, I just mean opposite of left. Okay, so that's part A. Part B asks, well, what if they were to stick together? What if they were to stick together? Well, if they were to stick together, I could go back into this equation and everything on the left-hand side of the equation stays the same, okay, down to here. And it's only after the collision that we, did I say equation? I meant equal sign. I'm getting dizzy here. I'm starting to pass out, but it'll be on tape. It'll be saved for posterity. Okay, so in this case, in part B, they stick together and move together. And when they're moving together, I can consider them to be one big ugly block of mass 4 plus 12 or 16 kilograms, moving at some final velocity. So if I put that in here, you see that this becomes very easy. I just have V final is going to be negative 16 franci over 16 kilograms, or negative 1 meter per second, or I could write that as 1 meter per second left. So that's part B. Part C asks us to find the change in kinetic energy in this second collision. Well, the initial kinetic energy is just going to be 1/2 times the mass of the small car times the velocity of the small car squared, plus 1/2 times the mass of the large car times the velocity of the large car squared. That's going to be 1/2. Okay, getting dizzy. Times 4 kilograms times 8 meters per second squared, plus 1/2 times 12 kilograms times 4 meters per second squared. And if I multiply that all out, what I find is that I get 224 joules. Now the final kinetic energy, since they're all moving together, I can treat them as just one combined mass of 16 kilograms. Notice that I didn't put the minus sign in here because I was going to square it, so it didn't really matter. Same thing here. I could put the minus sign here for the velocity of the combined mass, but I'm going to square that. And that's going to give me 8 joules. Now the change in kinetic energy is going to be the final kinetic energy minus the initial kinetic energy. Well, that's going to be 8 joules minus 224 joules, and that's going to be a negative 216 joules. So the fact that that change is a negative change means that it's lost kinetic energy, and that's what you would expect in a collision where they stick together. That we call a maximally inelastic collision. It's lost the most kinetic energy allowed by law. By what law? By Newton's third law. Well, now let's go to the last problem before I fall down. In this last problem, we have a kind of a hybrid problem. We've got a spring that's compressed, and it launches a block that is 2 kilograms. And once it gets launched, that 2 kilogram block is moving at a speed of 6 meters per second. And we're told that this spring was compressed a delta S of a half meter. And what we're looking for is this spring constant here. So that's part A. Well, this is obviously an energy problem. I had spring energy, and then later I have kinetic energy. And since this is a frictionless surface, you notice there's no hash marks there, there's no kinetic friction acting, the energy is going to be conserved. So when I start with the Grant-High energy equation, there's no work done between this initial state and this final state. Okay? So at the initial state, nothing's moving, so there's no kinetic energy. Everything's on the floor, so there's no gravitational energy. All of the energy is spring energy. When I get over here, I've got kinetic energy because something's moving. And the spring's not compressed anymore, so there's no spring energy. It's still on the floor, so there's no gravitational energy. So I can solve this for K. K, the halves cancel, and this is just going to be mv squared over delta S squared. And if I plug that in, it's going to be 2 kilograms times 6 meters per second. I've got to square that, and then I've got a half meter that has to be squared, and that gives me, I believe, 288 newtons for each meter. Now, we're told that there's a second block in this problem. It's a 4 kilogram block that is originally not moving. And that to the right of this block, there's a rough patch that has a coefficient of kinetic friction of 0.25. And we're also told that after this collision, the large block is moving. Okay, so after the collision, let's draw another picture. This large block is moving at 4 meters per second. And we want to know, how is that little block moving? Is it moving to the left? Is it moving to the right? Is it stopped? How fast is it going? Well, that's a collision problem. And so we solve collision problems by conserving momentum. Initial momentum is equal to final momentum for the system. And because this is a vector equation, we need the coordinate system. So we come down here for part B, and we say before the collision, we had a 2 kilogram block moving at 6 meters per second. It was moving to the right, so that's positive. We had a 4 kilogram block that was not moving at all. So I just wasted ink. And I'm not going to waste that ink. I'm just going to take that right out because I need the space. Okay, because that was 0. After the collision, I've got the 2 kilogram block moving at a speed that I don't know, so I just make it a positive variable. And then I have the 4 kilogram block moving at 4 meters per second in the positive direction. Now this is going to give me 12 Franci before the collision, and I better have 12 franci after the collision. Well, I've got this little block moving at a speed I don't know, but the big block has 16 franci. Whoa, well, both sides have to add up to 12, so that means this little block must be moving to the left. I'm going to get a negative answer here. If I subtract 16 from both sides, I get negative 4 franci is equal to 2 kilograms V final, and that gives me V final is equal to negative 2 meters per second, or 2 meters per second left. Okay? Now I'm going to erase part A here to get some more real estate. I don't know what's going to happen when I have to move these little exercises to my front room where I don't have a big whiteboard. Part C asks us for the kinetic energy before the collision. Well, that's just going to be 1/2 times the small mass times its speed squared plus 1/2 times the big mass times its speed squared. And you see that I just wasted ink there. Well, this is going to be 36 joules. If I look at the final energy, well, I have the small block moving at negative 2 meters per second. Got to square that. And I have the big block moving at, we're given that part, 4 meters per second to the right. And if I multiply that all out, what I get here is 4 joules plus 32 joules equals 36 joules. Well, looky here, I started with 36 joules and I ended with 36 joules. That means that this is an elastic collision. That's how we define an elastic collision, is a collision where the mechanical energy is conserved. And in this case, it was. Now, the last part of this problem, we want to know how far this block will slide before it stops. Okay? So that's a kind of a whole new problem. We don't care about the spring anymore. We don't care about the little block anymore. All we care about is the big block slowing down. So I have a big block of 4 kilograms moving at 4 meters per second. It hits this rough patch where mu sub k is 1/4, and eventually it stops. And we want to know how far does it go. Well, it turns out that's not what we want to know. Greg just made a mistake. You get your tuition back. Everyone gets all their tuition back. You are so lucky. What we want to know is how much time does it take to stop? Now, this is an honest mistake that Greg just made because there's 2 different ways I can ask the question. I can ask how far does it go, in which case this is an energy problem, or I can ask how much time does it take for it to stop, in which case it's a momentum problem. And on your exam, you should be able to solve either case. I could give you a problem like this and ask you, how far does it go before it stops, or how long does it take before it stops? In this case, in part E, we ask the question, how long does it take to stop? Well, we learned last week Well, not really, because last week was spring break, but the week before spring break, we learned that we never learned anything about time from an energy approach. That's just fundamental. That's just basic. And so if we want to find out about time, we have to use momentum. And because this is not a collision, it's just something slowing down, we can't go to this conservation of momentum equation. Momentum's obviously not conserved in this case. I had momentum and now I don't. So we have to go to the more general equation, that the initial momentum is equal to the final momentum, except when it's not. And it's not when there's an impulse, a force times a time. That's the Grant-High equation of chapter 8. Now again, because this is it's not a collision, we can't go here, but it's still a vector equation, so we still need our coordinate system. So initially, I had 4 kilograms moving at 4 meters per second to the right, so it's positive. I had a friction force that was acting on the block. Let's draw a free body diagram for that block. Well, the block has a weight force of 40 newtons. It has the normal force by the table on the block of 40 newtons. And then it has this kinetic friction force by the table on the block. And because that's pointing to the left, that's going to be a negative. Now, when the block grinds to a stop, it will have no momentum. So suddenly we see that we're almost done. If I just knew what this kinetic friction force was, it would just become algebra. Well, that kinetic friction force, table on the block, is going to be mu sub k times the normal force by the table on the block. That's going to be 1/4 times 40 newtons, and that's going to be 10 newtons. So now I've got 16 Franci minus 10 newtons times delta t is equal to 0. And if I solve that for delta t, I get 16 over 10, or 1.6 seconds. Okay? So that's the answer to the final part. If I had asked, how far does it travel? This would be part F, which is not actually part of this problem. Then I would use this equation. Energy initial plus Verk is equal to energy final. My initial energy would be 1/2 times the mass of the big block times its speed squared. This would be negative Verk by the friction force, 10 newtons, times the distance, and that would equal 0. Well, in this case, that would be 32 joules minus 10 newtons delta x is equal to 0, and that's going to give me a delta x of 3.2 meters. That wasn't part of the homework problem, but had I asked that on an exam, you should be able to work both of those problems. Okay, folks, I'm sorry for my dizziness. That's just part of being old. Again, stay tuned for a word from our sponsor. Stay safe, stay happy, stay healthy.